The ideal gas law, the atomic explanation of pressure. A balloon that is inflated with air has air molecules bouncing around inside. At the atomic level, nitrogen and oxygen gas molecules collides with the balloon's surface and it pushes the balloon outward. It is this outward force that causes the internal pressure or inner pressure. The ideal gas law describes the enormous number of collisions that cause the pressure within a container. This is what the ideal gas law says. The pressure in the container is proportional to the number of molecules on the container, the temperature inside the container, and the volume of the container. Just to stress this point again, this pressure is the pressure in a container. And the volume here is the volume of the container. If we didn't have a container, then we couldn't have a pressure because all the gas molecules would escape. The ideal gas law depends on three parameters: the number of molecules, the temperature, and the volume. To describe the ideal gas law, I'm going to use the PhET applet called gas properties. So what you're looking at here is that I have a container, and here's a thermometer. This is a pressure gauge that measures in atmospheres. And then here's a pump. And if I pump this handle here, what you're going to find here is that I'm going to get gas molecules that didn't come in. So let's go look at that. So I'm going to start pumping in some gas molecules. And what you're seeing here is that I have a pressure right here. Now note that the pressure here is fluctuating. It's not constant, and that's because the gas particles are moving randomly, and sometimes there's more collisions with the walls and sometimes there's less. So the pressure then varies. And then I have my temperature here that tells me that it's at 300 Kelvin. Kelvin is just a temperature scale like Fahrenheit. The ideal gas doesn't tell us what's going on inside. The only thing that it tells us about is the collisions with the walls of the container. That's what we're looking at. The collisions with the walls and the container. So here I go. If you look at the pressure, it looks like it's about 1 atmosphere. What happens if I put more gas molecules inside this gas container? But if I have more gas molecules, I have more collisions. More collisions means a higher pressure. So I'm going to come in here and I'm going to pump it. So now I've roughly doubled the pressure, I believe, and you could see that this thing is going up here. So instead of 1 atmosphere, it's now 1.5 atmospheres. So the pressure increased. Now if I want to decrease the pressure, I need less molecules. So I could come up here and I could open this thing, and what you're seeing here is that the pressure has decreased because I released the gas molecules. So now what you're seeing here is that the pressure has decreased because I decreased the number of gas molecules. So in summary, the number of gas molecules goes something like this. If I have more molecules, I have more collisions with the walls. But more collisions with the walls implies that there's a higher pressure. If I have less molecules, then that means I have less collisions with the walls. Therefore, I have a lower pressure. What I have here now is that I have a container again of gas molecules, and down here at the bottom I have a heat control. If I slide this thing up to add heat, I'm going to transfer heat energy or thermal energy into the gas container. So that heat energy then gets translated into kinetic energy of the gas molecules. If the gas molecules are moving faster, there's going to be more collisions. More collisions means a higher pressure. Let's go look at that. So if I add heat, look at the temperature, you're seeing that the temperature is rising. So as the temperature goes up, let's say I do it right here, what you're seeing here is that look at the pressure. It increased. But you can visibly see the gas molecules are moving faster, and if they're moving faster, there's a higher pressure because there's more collisions. Now, if I want to decrease the pressure inside the gas. Then what I'm going to do here is that using this thing, I could put this thing on ice. And you could see that the temperature is dropping, but at the same time, you're also seeing that the pressure is dropping. So a lower temperature implies that the molecules have less kinetic energy, which means that they're moving slower, and therefore they collide less, and I have a lower pressure. Number 2, temperature. Temperature is the average kinetic energy of the gas molecules. So if I have a high temperature, I have faster moving molecules. But faster moving molecules means that I have more collisions with the walls of the container. Therefore, I get a higher pressure. If I have a low temperature, then I have slower moving molecules. But if I have slower moving molecules, I have less collisions, and therefore the pressure lowers. So the last variable is volume. And the way you change volume is you look at this little guy right here. This guy has the capacity to make the volume larger or to make it smaller. Look what happens if I make the volume longer. So if I pull it away, what you're seeing here is that the gas molecules have to travel farther before they can collide. So what does that do? It decreases the pressure. If the gas molecules have to travel farther, then they're going to collide less. Now, if I decrease the volume, look what happens. You could see here that the pressure has increased. Why did it increase? Because I now have a container where the gas molecules have to travel less distance. And if they travel less distance, then that means I'm going to get more collisions with the walls of the container. Therefore, the pressure goes up. 3. Volume. So if I have a larger volume, they travel farther to hit the walls. Therefore, there's less collisions. Less collisions, lower pressure. If I have a smaller volume, then they travel a shorter distance before they hit the walls. Therefore, I have more collisions. More collisions means higher pressure. Example, can crush and temperature and volume. Let's start off by watching this video of the can crush by the Psy guys.
The equipment and ingredients you're going to need for this episode include an empty can,
a large bowl,
a set of tongs,
some water.
and a stovetop.
Because we're dealing with boiling water today, the safety equipment we're going to need include goggles, heat-resistant gloves, and an apron or lab coat to protect from spills or splashes.
The first step in our experiment is to take some cold water and fill up our bowl.
The second step of our experiment is to pour about 100 milliliters of water into the can. Turn your stove to medium-high heat and place your can with the water in it in the center of the burner. Leave it there until you see water vapor coming out of the top. Now quickly dunk your can into the water.
To explain this demonstration, I'm going to use the PhET applet called States of Matter. Before we get started, air is a very good thermal insulator and does not allow the temperature of things to change quickly. If you were to ask why does ice take so long in your freezer to freeze, it's because of the air in your freezer. It doesn't allow heat to come out of the water in order to make it colder to freeze. To change the temperature quickly, one has to remove the air inside the can. That is why water is introduced. When water is boiled, it pushes out the air molecules, leaving only water vapor. Water vapor can change its temperature quickly. Now let's go to the applet. So imagine that I have my can now. And what you're seeing here is that you're seeing water vapor molecules colliding with the walls of the can. Okay, so now what you want to do here is that when I take the can and I turn it upside down into the water, the gas molecules become liquid molecules. Look at what happens. So over here I'm going to click on liquid, and then you see that the majority of the walls of the can are not colliding with the can itself, and therefore the pressure inside is essentially zero. Picture-wise, I have the water vapor colliding with the walls, and so that's the pressure due to the water vapor collisions with the walls of the can. But at the same time, I have this atmospheric pressure that's pushing inwards. So now what we do is that we change the temperature very quickly by taking the can and putting it in cold water. That immediately collapses the water vapor into drops of water, and note that there's now going to be zero pressure inside effectively, but I didn't get rid of the atmospheric pressure. So what does the atmospheric pressure do? It moves from the high to the low region. So the pressure then goes from the high to the low pressure region, which then collapses the can.
760. Gewonnen hat Herr Dr.
A similar but different demonstration is putting balloons filled with air into a container of liquid nitrogen. This is known as LN2. Because LN2 is so cold, its liquid temperature is 77 K, which is the same as negative 331 degrees Fahrenheit. The gas molecules slow down considerably, reducing the pressure inside, and then atmospheric pressure does its work in collapsing the balloon. Here's a video. So what you're seeing here is that there's two balloons. It turns out that the one on the left is air, the one on the right is helium. And he's going to put these in a container of liquid nitrogen, too. And then here's the container of liquid nitrogen, too. Now he's about to take it out of the liquid nitrogen. And look how compressed it is. And now, as the temperature from the room heats up the air molecules, you could see that the air molecules are actually expanding the balloon again. In a very analogous way, the pressure inside the balloon and the atmospheric pressure outside, they balance each other out. But when I cool the air molecules inside the balloon, the pressure inside goes to zero, and then the atmosphere does its thing, which collapses the balloon. Volume effects on pressure. A suction cup works by changing the volume of a trapped gas. An image of this thing here is that I have a flat surface, and in violet right here I have a suction cup. Now inside the suction cup I have air. Once again, inside the suction cup there are trapped air molecules. But since I'm dealing with air, I always have the constant atmospheric pressure working here. To get the suction cup to stick to a surface, one lifts up on the handle of the suction cup to increase the volume. So then that means inside I have a lower pressure. Outside I still have the same high atmospheric pressure, so therefore it pushes the cup down. Atmospheric pressure pushes the suction cup to the surface. That's how a suction cup works. Number of particle effects on pressure. When you pump up a basketball or you add air to a car tire, one is adding more air molecules into the container. But by adding more air molecules, there are more collisions. This implies that the pressure inside is now larger. And that's how you could feel that the tire is stiffer or the basketball bounces more, because the pressure is higher inside that object.